Look closely at the back of any standard home router, right where the physical network cables plug in. Every local device connected to this piece of hardware, your laptop, your phone, your smart TV, is assigned a private IP address. These local addresses usually look something like 192.168.1.10. Inside your living room, that address works perfectly, but there is a massive mathematical catch. Millions of other homes and offices around the world are handing out that exact same address to their internal devices. This animated map illustrates the problem. If three identical 192.168.1.10 devices across the country all request a web page from the same internet server at the same time, it is impossible to know who should get the response. The public internet simply cannot route data back to an address that is duplicated millions of times globally. So if your device's address is not unique and it cannot be used on the open web, how is it capable of loading a public web page right now? The reality is, your private IP address is entirely invisible. It is completely trapped behind the walls of your local network, creating a strict boundary between the devices in your home and the infrastructure of the public internet. To understand how data crosses that boundary, you have to think about a network as having two distinct geographical zones: the private inside and the public outside. Sitting directly between these two zones is your router. It acts as a strict border checkpoint. And unlike your internal devices, the router has been assigned a single globally unique public IP address by your internet service provider. Watch what happens when you click a link. A data packet leaves your laptop, stamped with your private IP, 192.168.1.10, and travels to the router. Because private IPs can't survive the open web, the router performs network address translation, replacing it with a public IP. The consequence of this translation is that from the perspective of the destination web server, your laptop does not exist. The web server believes the request originated entirely from your router. NAT operates as a necessary disguise. It allows private devices to masquerade as the router, borrowing its unique identity to survive on the public internet. But borrowing that identity creates a logistical complication. In a standard home, a laptop downloading a file, a phone scrolling social media, and a TV streaming a movie, all at the exact same time, all sharing the router's single public IP address. When the data from those three distinct requests returns from the web server, it all hits the exact same public address on the router. The router now has to figure out which specific internal device actually asked for the movie and which one asked for the file. To solve this, the router maintains a NAT table, a high-speed memory bank logging every outbound connection. When returning data hits the router, it cross-references this table, restores the original private IP, and completes the delivery straight to your laptop. This high-speed ledger system allows the router to manage hundreds of simultaneous requests, preventing massive data collisions and ensuring every packet reaches the correct device. Because it happens invisibly in the background, NAT is frequently confused with other networking protocols. First, NAT is not DHCP. DHCP is the local protocol that strictly assigns your private IP address when you connect to Wi-Fi. It does not translate it. NAT is also not DNS. DNS simply acts like a digital phone book, looking up the destination IP address of a website so your computer knows where to send the data. DNS finds the address, but it does not move or translate the packets. And finally, NAT is not a firewall. While both live on your router, a firewall evaluates security rules to deliberately block or allow traffic. NAT is purely a translation mechanism. All these systems work in tandem to get you online, but NAT is the singular mechanism acting as the physical passport, inspecting and translating your data exactly at the border of your network. To grasp why this complex passport system exists, you have to look at the math shown in this scale visualization. We have tens of billions of connected smart devices globally, but the original Internet protocol, IPv4, only contains roughly 4 billion public addresses. NAT solves this global scarcity by functioning as the ultimate compression mechanism. A single modern home with 20 internet-connected devices only actually consumes one precious public address from that finite global pool. Without NAT's ability to multiplex dozens of private devices into a single public address, the internet would have completely exhausted its available space for new devices decades ago. Behind the seamless, instantaneous feeling of browsing the web lies an invisible, high-speed game of identity swapping, It happens thousands of times a second, right at the edge of your living room, keeping the global internet functioning every single day.